2, 1. So Pascal's triangle, which just keeps coming back, I guess, in grade 12, if you're studying this for your probability or data management course. I want to try to tie a few things in here and kind of go back to the binomial expansion with the use of Pascal's triangle, which I actually introduced in grade 11. And at that point, the Pascal's triangle, as you can see it here, you have seen it a few times. So I'm not going to explain the details to this, but I'll give you a link to the original binomial expansion tying it to Pascal's triangle. I'll put the link up above there. Now, once you learn combinations in grade 12 or some kind of a probability course where you have to do counting when there's no order, then something really nice happens, because the combinations that we write, so whenever we write a combination, so maybe n, choose r, or if you are used to writing it as n, choose r like this, or any other way. Once we know this, you actually can tie Pascal's triangle to this. So I'm going to just show you and the Pascal's triangle, so kind of row by row, as you can see. So row number 0. Okay, so this is, I'm going to the subscripts that you see there. So this 0 and the 0. So that just means the 0th row, okay? And then the second number, so the 0 is going to be the item in Pascal's triangle in that row. So for instance, this would have been the first row, and this is the 0 item. Okay, this is the first row, and this is the first item. All right, so we're going to always start from 0. And you can see this, okay, as it continues. So if you go to row number, let's say 4, it starts off, okay, so this is row 4, okay, and then we're picking off the 0 item, okay, row 4, we're picking the first item, okay, so as you can see, it's always row 4, and then second, third, and fourth. Now, the nice, interesting thing is, when you're building this Pascal's triangle, it's not very difficult, right? It's just the sum of whatever's happening above it. So for instance, 1 and the 3, okay, when you add those up, you're going to get your 3. And then if you add these two, you're going to get that 3, and then so on. So as you can do that. So you've seen that with Pascal's triangle. Now, as you keep going, it does get a little bit annoying, because if you have more and more rows, there's a lot more work to be done to try to figure things out. Now, in one of the videos when we were doing kind of ordered counting throughout, I did give you kind of the general expression. So for the term, so any term that you like is basically just the summation of the previous one, right? The previous 2, which you can have right here. The problem with that was that now you have to know the previous terms on the previous row. So what if we wanted to just find out, what this particular term in Pascal's triangle is without actually knowing the previous rows at all? And it turns out that in order to do that, okay, you instead don't need to know what the previous 2 entries are. You can actually use combinations, and this will be just if you are in the nth row, you can choose, okay, the rth item in that row, okay, and again it starts from 0, so it goes 0, 1, 2, 3 all the way up to n, and you will know exactly what this term is. So if you wanted to know, so for instance this right here, so notice that this is the 5th row, okay, and this would have been the second item. So if you do 5, choose 2, you're going to get this equal to 10 once you understand combinations. Now, this couldn't have been done before, because you would have to introduce combinations in some particular way to be able to get this. Now, Pascal, okay, originally with this triangle, just simply counted and trying to see. It started at the top and then was just doing the additions, and it nicely folded out. And then you had numerous applications to this Pascal's triangle, so from doing checkerboards, trying to see how many paths there are, to, all kinds of different other ones. I'll put up a link up above there to some applications if you want to see that. Now in this video, once we know that Pascal's triangle, every single entry that's there, it's just a combination, right? So n choose r, doesn't matter how deep we go, then it makes something really nice for us, where we can tie in that Pascal's triangle combinations to the binomial expansion. So what was the binomial expansion? Well, binomial, so this is one particular huge application, is that the binomial expansion just simply means that you take a binomial, which is a polynomial except bi, which means it just has two terms. Now it doesn't matter what those terms are, so I called it an x and a y, but they can be any terms, and I'll show one example of this. And now when you raise it to the nth power, you of course can do it by brute force, where you can just take this and multiply it and do the expansion. The only problem will be that you're going to have n of them. It's okay if n is equal to 2, and maybe even if it's equal to 3, right? So that's something that you can very quickly do. But when when n is equal to, let's say, 5 or 6 or maybe 10, and you're trying to do this expansion, then it becomes a problem, right? So how do we do this? And this ties in, and it's eventually called the Binomial Theorem, where it uses, and you can find out the coefficients of each of the terms by actually using Pascal's triangle, which we've seen in that first link that I was pointing out in the beginning of the video. But now we don't need the Pascal's triangle, because we can just simply use the combination and choose r. So for whichever one that we like. So I just want to show you how you can break this down. So instead of doing all of this right here by brute force, it is really convenient, okay, to just simply use the Pascal's triangle and, okay, the combinations kind of side by side. So let me just show you, okay, for these binomial terms, so these two particular terms, how this expansion would look like. Okay, so I'm going to take the term, and what it is your first one, so x, okay, and y, and it will start off, because you have, this is to the nth order, that first term is going to have x to the n, and then your y is going to be y to the 0. All right. Now there will be a coefficient in front, but I'll talk about the coefficient in just a moment, because that coefficient actually comes from that Pascal's triangle, so from that nth row. But now, as we have the combinations, okay, we're going to substitute and fill in the coefficient with a combination. So in just a moment. So this will be now plus, all right, and then it would go x. Now it's n minus 1. Now the y is going to be increasing. Okay, so notice it goes n, then n minus 1, while the y starts from 0 and then it increases to 1. And then it continues on, so it would have been now x n minus 2, y is going to be 2, and this keeps on going until, eventually, so this will be now x, so this is the dots, that's where you see that. So x may be n minus r, and then this would be y to the r. So notice whatever you are subtracting on the x term, okay, will be now the actual exponent on the y term. And then this keeps going, eventually until you're done. So then this would have been x, you eventually exhaust these, so this comes to 0, and then y is going to be n. And now we have, we need to know what the coefficient here is, right? So for all of these, what that coefficient would be. Okay, so that coefficient, because we are now dealing with so this is like saying that this is the nth row in Pascal's triangle, okay, so whatever that might be, but we know what those values are. We can just simply now use the combination right here. So we are in the nth okay, so this would have been n, so my coefficient, okay, is going to be, and now what you have is you start from the beginning. So if you imagine that it's maybe the 5th kind of row, so it would have been that 5, you know, choose 0, and then the next coefficient would have been 5, choose 1, next one is 5, choose 2, until eventually you exhaust them. Now for here, so I'm going to kind of remove this and highlight it so that you can see it. So that is your n, okay, so that's going to be there. And then this right here, okay, so that's right there, okay, that's going to be, okay, the value that you are actually choosing, which is the item that you are in that Pascal's row. So for here, so this, my first one is going to be n choose 0. Now the second one, because we are in the nth row, so this always will stay as n, okay, and then you're going to be choosing the first one, so that's actually coming from here, and then the next one would have been n, all right, this is now 2, so that is from that, so it's the exponent on the y, and so on until eventually, you know, so this would have been n, okay, choose r, right there, and finally, you know, this is going to be n, choose n, all right, okay, where we have that. And this is actually the binomial theorem that you have for a binomial expansion, where these are called, so these ones, these are called your binomial coefficients that you have within here, and you can use, you know, n choose r to be able to find those coefficients instead of actually going back to Pascal's triangle. The coefficients are actually coming from Pascal's triangle, but it ties in to the combinations, which now is much easier, so that you don't have to create a Pascal's triangle for yourself when you're doing this. You can just say, oh, the coefficients were just simply, you know, n choose r, okay, and then you can pick whichever ones that you are writing out. So let's try to apply it, and let's give one particular example so you can see that it's kind of peeking out there. So this is like saying that we have, so this would have been my first term, all right? So this is like saying this is that x, all right, within here. Now we want it to be plus, so we're going to suck in this negative, all right, and the 3a. So that would have been, okay, so this is like your y, okay, and then my n is to the 5, where your x is equal to 2x, okay, from here, and then your y is just simply equal to negative 3a, all right, and that's coming from there, and now your n is equal to 5, which we can now expand. So in order to expand this, what we would do is we would say, so I'll do the first few and then I'll finish it off kind of in fast forward fashion. So what I would do is I would say, all right, so we have 2x, all right, so we're always starting, so this is going to be to the 5, multiplied by y, which is negative 3a, this is to the 0, right, which is going to be 1. My coefficient in front is going to be n, which is 5, choose 0, so that's just equal to 1. So that is your first term. Now it's going to be plus, all right, and now we continue. So now my second term, so 5, 1, so that's my coefficient. Okay, this is 2x, now it's 5 minus 1, right, which is going to be 4. And then my y, which is negative 3a, so this is to the 1. So that is what we have there. And then again, so we can continue. So I'll kind of do it on the next one. So this would have been 5, choose 2. 2x, this is 5 minus 2. Negative 3a, this now becomes 2. And, you know, I can continue this. I'm going to do it in fast forward fashion and then come back for you. All right, so here we have it. So that's the entire expansion. And now, of course, you would have to compute these out if your teachers wanted you to do that. So, you know, you know what this is, you know, so this is going to be just equal to 1. You can now apply the exponent, so 5, so it's going to be 2 to the 5, right in front of there. This is just going to be equal to 1. So, you know, so this entire whole term that I have, that first one, so that's just 1. 2 to the 5, which I guess is 32, right? So this is going to be 32, and then this is x to the 5, and that's going to be your first term. And then you would do the same thing with your second one. So you would find out exactly, you know, what this equates to. And then you would have your second term. So 5 choose 1, which is going to be 5. And then it's going to be 2x to the 4. Okay. So, so that's going to be, I guess, 16. And then you have the negative 3a to the 1. So that's going to be negative 3. And you have to now multiply that 5, the 16, the negative 3. And then you're going to have x to the 4, and then a to the 1. And then you would continue that for every single one so that you can do your actual expansion. It's still work, but it actually is a lot less work than doing just brute force and doing expansion, you know, with 5 different terms. So a binomial, okay, except multiplied by itself 5 times, it would have been extremely annoying and very lengthy. So this just gives you a little bit more of an idea how to approach this. So it ties in, you know, the Pascal's triangle, ties it in with combinations, okay, because those become your binomial coefficients now for the nth row. And then you can attach it to this binomial expansion, which is an amazing application to be able to do that. All right, so I hope that you understood what I was trying to explain here. It's kind of the last time that you probably will see the Pascal's triangle tied in within the video series, but you might see quite a lot of applications down the line. All right, so thanks for watching. We'll see you in a future video. Bye, everybody.